And I can tell you it's 37 years of sheer fun. Every day when I come to work, I still have a smile on my face. My name is David Warshaw. I'm the professor and chair of molecular physiology and biophysics at the University of Vermont. My lab does biomedical research on genetic forms of heart failure. My lab has about 10 individuals, and those people can be anything from students to postdoctoral associates to faculty scientists to optomechanical research engineers. The instrumentation that we use allows us to measure forces generated by tiny proteins, and one protein in the heart that makes your heart beat is called myosin. It interacts with actin, and actin is sort of this rope that myosin grabs onto. Well, we can measure force in a single myosin molecule. It generates about a piconewton of force. How much is that? I'll give you an example. If you shine a flashlight on a penny from a yard away, the photon pressure on that penny from the flashlight is 1 piconewton of force, okay? It's pretty tiny. So you've probably seen stories in the news about a basketball player dying at the age of 22. They do an autopsy, the heart's enlarged. What happens is if you do the genetics on it, it's the mutations to this tiny molecular motor called myosin. Everybody assumed that the motor, because it's mutated, is broken, therefore generates less power, and therefore the heart enlarges because of that. Well, one day we're in the lab, using the instruments we do, we measure the force and power generated by one of these motors that's been mutated, and it generates twice the power as normal. And then we realized everybody was thinking about it totally wrong, right? It's that it's overpowered. It's like putting a Ferrari engine on a Volkswagen chassis and going to the racetrack. That's not going to be a good situation. And so the heart, if you then look at the heart, it's actually enlarged because it's scarred. It's more scar tissue than increased muscle mass. And so the onus was on us to prove that, in fact, we were seeing what we were seeing. Since then, numerous investigators have rediscovered the same thing. So the interesting thing is there are companies out there now that are designing drugs to sort of power down these motors. And I can say we were involved in finding that. But I can tell you a quick story, if you don't mind. So we're talking, well, 1991. One of the instruments that we built at the time was called optical tweezers or laser trap. Our optical design engineer, Guy Kennedy, who's been with the lab for as long as I've been here too, we built one based out of optical filters. But the interesting thing is that this microscope has so many different light paths and so many different wavelengths of light, meaning different colors of light, that you have to keep track of them, and they overlap. And the only way you can make that happen was with the design of special filters. We contacted Chroma, and that was, the design was so intense that I don't think we could have actually described it well by phone. And so we said, do you mind if we drive down and we'd like to pitch this design? And we figured, being Vermonters, beer wouldn't hurt, and that we can maybe entice Chroma to get us these filters ASAP. Because when you do biomedical research, you can't wait till tomorrow to get something done. You always say, it should have been done yesterday. And that also plays out when it means purchasing anything from any company. And I have to say, Chroma felt that urgency just as much as we did. I can tell you, we were shocked at how quickly we got those filters. So that's 19 years or 29 years. 29 years. We've only purchased Chroma products. And that relationship has been strong and consistent from that day, first day on.